All right, in our final look at how we treat measurements here, we need to consider significant figures. So significant figures are really, really important for two reasons. Because first, they make the number more palatable, a little easier to carry around. We don't want to be carrying around 10 digits after the decimal place. It's just not convenient. But secondly, it's really incorrect to carry around that much. Because let's say that we have a ruler, right? We're using a ruler to measure things, and it's got the little tiny lines on the ruler. We might be able to get halves of an inch, and we might be able to get sixteenths of an inch. But can you truly use that ruler to determine the length of something to the thousandth of an inch, to the millionth of an inch? That's what you would be implying if you show all of those figures after the decimal point, that you really understand that this is the level of precision of that instrument and it is accurate and precise enough to get that much information. Okay, so that's the big picture of significant figures. I really recommend you keep in mind. The general rules, though, all non-zero digits are significant, leading zeros are not significant, and trailing zeros tend to not be significant either. Again, these are placeholders. They're not actually measured, right? This is like if I'm saying, that from here to where I'm going is 21 kilometers away. I might not know that it's 21.3 kilometers or 21.1 kilometers. To the best I know is it's 21 kilometers. And likewise, the best that I know is it's 21,000 meters. I would not be able to tell you that it's 21,500 meters, right? And so if I wanted to express it in meters, I need the zeros to show that it is in a meter unit, not kilometers, but I didn't measure them. They're not significant. They're just placeholders. Okay, so how does this look in practice? Let's look at a few examples. If I have the following numbers here, 0.00560, three significant figures. Which ones of these are significant? Well, it's the 5, the 6, and the final 0. The 5 and the 6 are obviously significant because they're non-zeros. They were measured because they're here, so they're significant. But why is the trailing 0 significant while the initial zeros are not? Well, the initial zeros are placeholders, right? This is showing that it's 5 thousandths, basically, right? 0.005. We cannot really express this number in this form without having those placeholder zeros there, but they were not measured. This would be like if I'm trying to convert 5.6 grams to kilograms. Yes, I need to move the decimal to convert to kilograms, but now that I've moved the decimal and placed those zeros, they are not actually measured. They're just holding the place to enforce our unit. And likewise, that trailing 0, well, that's not a placeholder, right? We could remove that 0 and we'd still have the same value. However, this one is significant. So the last 3 digits in the top example are significant, 560. They're significant because we have measured it, right? If this is grams converting to kilograms, we had some instrument that said this is 5.60 grams. We measured that final 0. It wasn't 5.59, it wasn't 5.61, 5.60. We earned that significant figure through measurement, and therefore we want to carry it forward. When we have more significant figures, it often allows us to report more precise results moving forward, and we want to be able to track them properly. Second example, 12.300, same thing. We have some instrument that's measuring all the way to the thousandth place. Maybe we have a supervisor that has a incredibly precise milliliter, thousandth of a milliliter volume measurement that they spent a lot on in order to get for our hospital. And we've measured out that it is exactly 12.300 milliliters. Well, we don't want to just drop off those significant figures. They paid a lot for those significant figures. This instrument measures it very precisely. It just happens to be that the precise measurement ended on 00. It could have been 12.299, right? If it was a tiny bit less, but it wasn't. It was 12.300. Whether it was 12.299 or 12.300, it's still 5 significant figures. These zeros are marking that that is the value in that placeholder, and they are not just there to make the unit work out. They're not placeholders, in other words. They were actually measured zeros. And that's the key to significant figures, is that when a 0 appears, Is it there because it needs to be to hold a place? Probably not significant. Does it seem there redundantly? Well, it's probably not redundant. It was probably actually measured. Okay, when we deal with significant figures in calculations, it's really important that we know how many we started or ended with, because when we multiply or divide numbers, our result is only going to be able to have as many significant figures as the least number of significant figures in our calculation. So let's say we're tracking miles per hour, and we know that we traveled 351.2 miles in the span of 5.5 hours. We do the calculation, and we get our speed is 63.854545 miles per hour. We cannot report 63.854545. It is too many significant figures. We are limited by the precision of what we started with, right? So what we started with is miles and hours, two different values here. How many sig figs in miles? Sig figs, significant figures. How many sig figs in 5.5 hours? So take a look at those, determine how many each of those have, and then note that whichever one of those has fewer sig figs, that's the number of sig figs that we have to report in our final result. Okay, let's take a look. 2 sig figs is what we're dealing with, right? If we look previously, 351.2 miles, that's 4 sig figs, 5.5 hours, that's 2 sig figs. And so when we consider these, we say, well, our answer has to have 2 significant figures because that's the smallest amount of significant figures that we have from our source information. And as a result, our answer has to have 2 significant figures. We need to round to 2 significant figures. When rounding, if it's a 4 or lower, we round down, right? 4 is closer to 0, so we get rid of that. But if it's 5 or greater, then we round up, and our answer here should be 64. Please don't just drop off the significant figures that we cannot use. We need to round these appropriately. 63.854545 is the calculated value, but remember that this really doesn't have any meaning. What this means is that the closest to significant number we can report is 64, and that's what we should report. Reporting all these significant figures is not like better, it's not extra work, it's just wrong, to be honest. We need to have the precision of our final value show the correct number of significant figures. Okay, adding and subtracting, things are a little bit different, right? Multiplying, dividing, we just take the smallest number. But adding or subtracting, we need to look at the actual decimal place that we're dealing with. So here, if we are looking at a difference, right? 10.11 kilograms minus 3.6 kilograms. In the first bit of information, we have 2 decimal places, and in the bottom we have 1. Our final value can only be tracked to where we have the least number of decimal places. So in this case, it's 1 decimal place. We do our calculation, we get 6.51, but we have to report 6.5. We cannot keep that final value. It is just not precise from the information that we've used. 6.5 kilograms is going to be our answer here. And again, right, the idea is that we cannot report values that we didn't use. We don't know that the 3.6 wasn't 3.58 or 3.62. We just know that it's not 3.7, it's not 3.5. Therefore, we can't report that hundredths place, the second number after the decimal, when we subtract these two. Okay. Finally, scientific notation. So again, I think that with a lot of examples in sig figs, it's pretty clear. But when we have these placeholder zeros, things can get a little bit more confusing, right? If we look at these two values, both of these at the top, 250000, 250,000, this is 2 sig figs. Those zeros are simply placeholders. 0.000036, this is 36 millionths. Those first zeros are also not there. We didn't measure those. Those are just placeholders. So 2 sig figs for both of these. And if we want to express this in terms of a way that really communicates that it's 2 sig figs better, we're going to break it down into 2 parts. So again, that first example is 250,000, right? Or 2.5, hundred thousandths, right? That's what we're going to be communicating this as. We want to show it in terms of the significant figures, so 2.5 times 10 to the 5. 2.5 10 to the 5 indicates that we move the decimal 5 places over, and so that's how we're going to express this. In the bottom, 2.5 times 10 to the 5 and 250000. These are identical numbers, but in the bottom, we've rolled all those placeholder zeros into a 10 to the 5. And remember that that little exponent, right, that means 10 multiplied by itself 5 times. So it's 10 times 10 times 10 times 10 times 10. That is those zeros, right? So they're the same number, we're just communicating them in a different way. If it's 10 to the negative 5, that means the decimal's moving in the opposite direction. So our answer is 3.6 times 10 to the negative 5. That 10 to the negative 5 indicates that we need to move the decimal 5 spaces to the left, and then that would recover our original value as well. Again, they're just different representations for the same number, and the scientific notation form is really important to know because it allows us to track things, firstly, by watching our significant figures and what we actually measured properly, and secondly, by just being more compact and not needing a bunch of zeros. If the situation is more extreme and we need to carry around like 50 zeros, that would really be cumbersome to communicate. Containing it as times 10 to the 50 is just much clearer when we have more complicated solutions and is an important thing to know here.